Dear Michael, dear President, dear colleagues, dear students, family and friends, I have the pleasure to introduce you to the inaugural lecture of Mickael Perrin. I just learned that Mickael Perrin's parents grew up in the valleys, but he himself grew up in the Amsterdam region, and that's why he had his bachelor and master thesis degree been awarded in the field of applied physics at the University of Delft, the specialization in quantum and nanoscience. He then continued in Delft with the PhD from 2011 to 2015 in the group of Professor Herr van der Zandt. The topic was again something very special, single molecule electronics. And the thesis title was Charge Transport through Single Molecule Junctions, Experiments and Theory. He continued with a postdoc at the very same institute before he was given a position at EMPA. He joined EMPA in 2017, and in 2020 he was awarded a permanent position. He joined the lab of Professor Mickael Perrin on the transport at nanoscale interfaces, and this actually was also where he started in his work on nanoribbons. In 2022, he was awarded the URC starting grant. He was awarded a SNS Excellenza Professional Fellowship, and that's why he has now become a professor with us at the Electrical Engineering Department. I've been told this was not the only award that he received. He also received the prestigious award for his PhD. He received an award for having handed in the best PhD thesis at Delft for the year 2016 and 17. Michael, the stage is yours. Welcome.
Jörg, thank you very much for the very kind introduction. And thank you, everyone here, for being here. It's a pleasure to see so many friends, family, colleagues here in the audience. So I joined ETH here in June last year, and I have to say it has been a wonderful journey since. And for that, I would like to start with thanking all the members of the department. So in this lecture here today, I will explain you a bit, what type of research I'm doing, what I'm doing now, where I would go, let's say, in the future. And the title here is When Quantum Mechanics Meet Thermodynamics. So what I would like to, explain to you, and maybe I hope to convince you of, is that, these two very different fields of physics, I think there is a good reason, to somehow put them together. And this is what I would show you in the next, let's say, 45 minutes. So in the first part of the talk, I will talk about, it's going to be about the quantum mechanics, and then towards the end, I will also introduce some thermodynamics. So I would start with the quantum mechanics, and with that, I would start with a very simple example that everybody here knows. These are, let's say, the chips that you have, for instance, in your smartphones. You and I we all have them. And these ones have been evolving tremendously in the last years, and I think one way to nicely illustrate this is to show you, a picture like this one. So these are two video games. One of them is from the 80s. It's Prince of Persia, so it's 2D. It looks 2D. You can count the pixels, and then on the right side you have a video game from this year, which is photorealistic with a great amount of details. And this was all enabled by the increasing performance of computer chips. And at the core of the computer chip, you have the transistor. So the transistor is a small on-off switch, which, if you put them together, you can perform computation. So this can be just a simple mathematical operation, but it could also be, calculating the color of each of the pixels in the image. And what we see is that, in the last decades, because, starting from the 50s, what we see is that, every decade, the number of transistors has been increasing tremendously, and it's fair to say that easily a factor of 10, let's say, every decade, even more. And this trend is a bit easier visualized in this graph here. So we have on the x-axis we have the year, and on the y-axis we have the number of transistors. So in the 70s we were around, let's say, 1,000 transistors, and now we are about 100 billion, and if we continue like this, we will be around 1 trillion by the end of the decade. And this, of course, I mean, to fit everything on a chip, well, these ones had to become smaller. And so the transistors in the 70s, they were a couple of micron, so about, let's say, 1/10 or 1/20th of the size of a human hair. Nowadays, they are, well, nanometer. And so a single nanometer is a very small length scale. And just to give you an idea of how small that is, I would like to start here with the planet Earth. So it has a diameter of 10,000 kilometers. If we scale this one a factor of 100 million, we end up with 10 centimeters, which is the size of a soccer ball. If we scale it again with a factor of 100 million, we end up with a buckyball. So this is a small molecule, which is a single nanometer. So this is how small a single nanometer is. And at this scale, what you would see is that you can really start to see individual atoms. And that also means that, well, the classical laws of physics, they stop to hold, and we have to treat everything using quantum mechanics. So this trend here, by this downscaling trend, I don't know how it's going to evolve, but I mean, we start to, let's say, reach the limit of this downscaling. And there are different, let's say, ways this is going to, continue. The first one is, well, look, we will just continue for the moment. At the moment, everything is based on silicon, which is more like a three-dimensional material, but we can do. There is an entire class of materials, which is very thin, layered materials, which are just 0.3 nanometers. So it means that, by going to these type of materials, we could, well, already gain a factor of 10, let's say, in terms of transistor size. So this is one approach. What could also happen is that we start to have more functionality on these chips, right? So we could have on-chip sensors. We could replace some parts of this chip that perform a specific function with just a single component instead of having many transistors. This is one way. We could also think about completely different ways of doing computing. For instance, using photons. So instead of using electrons like the regular chips, we could use photons, which would make everything, well, much faster. Another approach would be to, for instance, neuromorphic computing. That's, again, a very different way of doing computing, which is based on how the human brain works. So what is remarkable about the brain is that it can perform really complex tasks at just a fraction of the cost of the energy cost, of the power cost of nowadays chips. And then in a brain, so instead of having transistors, you would have, artificial neurons. So this is, again, another approach. But what we see is that when we really go to the atomic limit, that, the big problem becomes, these quantum effects. Because, chips behave differently. We could also, have technologies that, explicitly exploit these quantum effects. And these are the quantum technologies. And so this is the field where I'm working on. And so there are different types of... something is wrong with my remote, sorry. So there are different types of quantum technologies, and here I would like to list a few of them. So quantum computing, quantum communication, and quantum sensing. So each of them here is very well represented at ETH, and I would like to briefly highlight each of them. So the idea of quantum computing is that by using quantum effects, we can perform calculations which are unfeasible or completely impossible with classical computers. So as you can imagine, this would have a lot of application, well, for research, but also for the discovery of new materials, discovery of drugs, but also in terms of, it's supposed to be able to solve very complex problems. So anything which is related to finance, the logistics, big data could benefit from this. Then we also have another field, which is quantum communication, and there the idea is that using quantum effects, we can create networks, communication, which is ultra secure, which you cannot hack. So also there, in terms of applications, governments, military, banks, big corporations, they would all be very interested by this kind of technology. Then we have quantum sensing. So in quantum sensing, the idea is to make sensors which are much faster, much more accurate than, let's say, classical sensors. And because sensors are pretty much everywhere, this would also have huge applications. And so this is, these quantum technologies are not very, they're not new, but what you see is that, in the recent years, there have been a huge amount of investments made. And here I would just like to show you a map of all the investments at the national level, into quantum technologies. And so this is the data from last year. What we see is that 30 billion was invested by national governments into this quantum technology. So that's a huge amount of money. And we see the same trend when we look at multinationals. Think about Google, IBM, Intel, Microsoft, and so on. Same also for the amount of startup companies that is being founded, based on different types of quantum research, or quantum applications. So with all this money, what actually happened is that in the last decades, this quantum research, well, it used to be something which happened, let's say, in the basement of the physics departments of the universities. There are now entire institutes, both in the public and also in the private sector, that are being dedicated to this type of research. So this research is, this quantum technology is all based on quantum effects. And so besides having these quantum effects, what we usually also need are materials in which we can host these quantum effects, in which these quantum effects are very strong. And this is what I would call here a designer quantum material. So these are materials which ideally we can design, which have really strong quantum effects. And what I mean with designing, it means that we can change the chemical structure such that we can influence their electronic, optical, and magnetic properties. And ideally, even up to the atomic level. So it means single atom precision of how we fabricate these materials. And well, because every atom matters, it also means that what we need are materials which are ultra clean and also defect-free. And there are many materials which are being worked on. So the first one, for instance, the van der Waals. So these are the two-dimensional materials I mentioned before. But there are quite a few more. One of them I would like to emphasize here are the carbon-based materials, and this is one of the fields where I am working on, and this is why I will explain a bit more about these ones. So these carbon-based materials. So this is what I'm working on, and this brings me slowly, let's say, to the topic of what we do in my group. So I'm here at ETH professor on low-dimensional quantum electronics, and the aim is to integrate these designer quantum materials into electronic devices. So electronic devices and also thermoelectric devices. So in practice, what it means is that we take these materials, we put them into devices, we characterize these devices, and then the aim is, to exploit these quantum effects. But one particular aim I would say is also to try to have these quantum effects, also at room temperature. So because usually all these effects are, they need very dedicated, low temperature measurement. So one of the things I'm interested in is also to have this at room temperature. So besides being a professor at ETH, I'm also a group leader at EMPA. So there I had the Quantum Devices Group, which is part of the Transport at Nanoscale Interface Laboratory, which is headed by Mickael Perrin. And so my group works, on these different topics. So one of the things I would like to mention here is because, they do all the work, is just to show a picture here of the different group members. So this was a picture from last group outing that was last year. So since then we had, we had a few different new faces. We had, not everybody could make it here, so there are a few more people here I would like to, emphasize. That are part of the group. There are also a few more people I would like to mention here, which are former group members, which in one way or the other contribute, significantly to the research I'm doing, which I also would like to mention here. And I'm happy to see that, many of these people made it today. So thank you all for being here. Thank you, for the great efforts you've put in this research, in your support, particularly also Mickael Perrin, and I'm happy to see all of you here. I would now go back a bit to these carbon-based materials, explain a tiny bit more, what I mean with that. So here I show a few examples: graphite, diamond, carbon fiber, all based on carbon, but actually there are many more. There are many more in different types of shapes, sizes, and so on. I would like to highlight a few here. Graphene nanoribbons, molecules, C60, so the buckyball I mentioned before. So these are materials that we work on. They are very interesting materials, and one of the things I would like to try to give you a feeling for is why these ones are so interesting. So these carbon-based materials, as you can already see from the amount of different materials, The chemistry is very, very well established. It means that many different types of materials can be produced with a large range of different types of effects. These can be electrical effects, mechanical, thermal, and so on. Just to give you an idea, take, for instance, diamond. Well, it's the hardest known material. Take graphene or carbon nanotubes. These are the strongest materials that we know, and it's all still extremely lightweight. Take graphene again. It's the material with the highest thermal conductivity. So in terms of physical properties, they have remarkable properties. Besides that, carbon is a very abundant material, so it makes it also much more sustainable than any technology which is based on heavy metals, rare earth compounds, and so on. And then one of the important points here is also, these quantum effects can be very strong. And this is what is important, let's say, for our research. So I mentioned already several times quantum effects, but I haven't actually, explained what these quantum effects are. So there are many, and I would like to just show a few here. So in quantum mechanics, everything is described by, this equation here, that's the Schrödinger equation. So this equation actually tells us that everything, for instance, also electrons, behave as waves. So what does it mean? Well, it actually means that everything can be at many places at the same time. So an electron is not, at one position, it's at many places at the same time, but each with a different probability. Sounds maybe a bit strange, but if I make the analogy with, for instance, let's say you take your smartphone, but you lost your smartphone. Where is it? Well, it could be, there is a probability it's just in your pocket. There is a probability it's just, on your desk. There's a probability it's somewhere else. See, so this lost smartphone has, a distribution in space of where it can be. So the electron is the same. The electron has a specific, spatial distribution. And based on this wave nature, there is another effect which is very important. That's quantum tunneling. I would like to make the comparison here with Swiss mountains. So if you have a nice Swiss mountain, you want to go from one side to the other side, you have to go up, you have to go down. In quantum mechanics, you don't have to do that, you can just go through. It will be the equivalent of making a tunnel, but you don't actually make a tunnel, you just go through. And this is quantum tunneling. There is a third effect here, which is quantum entanglement. I would like to emphasize a bit. So when two particles are entangled, they somehow share a connection. And this connection, well, it's quantum in nature, but one way maybe to nicely illustrate this is to take a pair of socks. Sounds strange, but let's say you take a pair of socks and you put one on your left foot. The other sock is instantly, no matter where it is, it's going to be your right sock. And in quantum mechanics, entanglement works in a very similar way. And as you can imagine, something like this, an effect like this, would have, let's say, nice implications for quantum communication. And it's actually one of the areas where it's heavily being used. The fourth effect I would like to mention here is quantum confinement. This is also the effect that makes your nice quantum dot LED so bright and so colorful. And this is one I would like to illustrate a bit more. So for that, I will show you, this picture here. So this is the picture of an atom. This is an atom. At the core, at the nucleus, we have protons, we have neutrons, and then around it orbit electrons. And these electrons have well-defined orbitals. Each of them have well-defined energy. So in the end, we only have specific orbitals which are allowed, specific electrons which are allowed with specific energies. Some of you who have kids may actually recognize this picture. It comes from this book, Quantum Physics for Babies. And this is here my youngest daughter who is reading it. So this book, of course, is a simplification of reality, but it is correct in the sense that there are well-defined orbitals, and each of them have well-defined energies. The thing is only that these orbitals are in practice just a bit more complex in shape. So here I show some of the orbitals for the carbon atom. And then once we have these orbitals for the individual atoms, we put them together in molecules. So these are the different energies. So each orbital here has a different energy. Once we put these orbitals together in molecules, we still have these orbitals. They just become more complex. Another effect, what you also see is that these energies, they start to they go a bit closer to each other. If you make the molecule even more large, orbitals become even more complex, energies go towards each other. And this is actually a result of quantum confinement. So quantum confinement tells you that once you have an electron and you put it in a very small box, you get these very specific orbitals. So the smaller the box, the more spread out these orbitals are. And this is why also, something like this laser pointer here, it doesn't have quantum confinement because it's very big. Everything which is very small, like individual atoms, they would have a very, let's say, quantum confinement would be very, very strong. And this is one of the things which is interesting to study, are single molecules. So what I did during my PhD, which I did in the Delft University of Technology with Herr van der Zandt, what I did there was taking single molecules, put them then in an electronic device, and then try to realize a functionality with these molecules. So one of the functionalities I worked on was how to make a diode, or also make a resonant tunneling diode. And this is all based on the single molecule. And there are other types of functions that people have been doing, but this is what I worked on mostly. These molecules are, they're very nice. They're very small, and this is why these quantum effects are, so pronounced. It also makes it, of course, very, difficult to integrate them into a device. At least to do it, let's say, reproducibly. And as I mentioned before, this is single molecules. Single molecules, single nanometers, so it's really small. So at the moment in the group, we're studying different types of materials, but there is one I would like to highlight in particular. So these are the graphene nanoribbons. So I mentioned already graphene before. So graphene is a single layer of carbon atoms, so it's very, very thin. It's two-dimensional in nature, so it's a fully extended plane. And then what you can do is you can shape this plane into ribbons. And each of these ribbons can have different edges, and based on the edges, it would have different quantum properties. And what is nice here is that you can have many different edges, so also many different types of quantum effects. Another thing which is useful is that the size here is not a single nanometer, it's more like 10 to 40 nanometers. So in terms of device integration, it's it's a bit easier. On the other hand, the synthesis of these guys is very complex, and it happens in extreme environments, so that, on the other hand, complicates things again. So for this research here, I would like to briefly mention the lab of Roman Fasel, with whom we strongly collaborate. So, they have been synthesizing these ribbons for us. Special thank also for Gabriela, who has been synthesizing many of these ribbons for us. So this is ongoing research here. And one of the things I would like to point out here is that if we think back about these designer quantum materials, about single atom precision and so on, this is one of these materials where this is very well manifested. So these ribbons here, they are grown from small molecules, which you put together, and then they form this chain. So you just put single molecules, it forms a chain. This, of course, is a nice, just a nice drawing. In practice, actually also they behave like this. So this is a picture of an ultra-high resolution microscope in which you can really see individual bonds and individual atoms, and you can see that you have this single atom precision. So we take these materials and then we integrate them into devices. So a typical device, or a device could look like this one here. So these are all electronic devices. What we have is, on the right side, let me illustrate this one. We have the graphene nanoribbon, which is a sandwich between these two blue protecting layers, and then can contact it from the side by two metal electrodes. So what we do with these devices is, in the most simple case, we apply a voltage on one of the electrodes, and then we measure the current on the other electrode. And then typically we also have a third electrode at the bottom, which we call the gate, which can be used to, let's say, remote control the properties of these ribbons. So these are now, this is just a nice illustration. And now I would like to show you the actual device. It looks very similar, where we still have, the two electrodes on the side, the ribbon in between, nicely protected nicely protected by these blue layers. So this is how these devices look like. So this is a big part of what we do, is really integrate these materials into devices. And one of the things which is impressive about this particular device is that if you look at the geometries in terms of sizes, we are really talking about, close to single, nanometer scale. So, fabricating the device is a huge challenge. So once we have these devices, we characterize them. And for that, we measure the current, while varying the applied gate voltage, and also while varying the gate voltage. And then what we see are these types of colorful maps. So these are complicated to understand on first sight, but one of the things which is interesting about these ones is that once we have a good device, we would see these diamond-like shapes, right? So you see these white diamonds. So usually when we see these diamonds, it's nice. So when one of the team members comes, I've got nice diamonds, then we look at it and it means it's a good device. I will explain, briefly why we're interested in these diamonds and what they actually mean. For that, I would like to rotate this picture here, and then I would like to take a line cut, along this orange line. So what we see here is that the current, the conductance here, it goes from blue to red to blue to red and so on. So when it's blue, there is no current flowing. When it's red, there is current flowing. So what we basically have here is a filter for electrons. So at specific gate voltages, there is current, at others, there is no current. And what is interesting here is that these gate voltages are actually proportional to the voltage. So sorry, to the electron energy. So what we have here is a filter which blocks electrons at particular energies and lets them through at other energies. Okay, so this is nice. We have a very good, very efficient filter. The question, of course, what sets these filter properties, and can we somehow, influence it? Well, it turns out that these are the orbitals. So once we understand how these orbitals work, we can see how they behave in these devices. Vice versa, from these measurements, we can understand what the orbital structure is of the materials that we have in the device. So this is, let's say, one particular example we studied, but depending on, let's say, the needs and requirements of the devices, we would have, different types of device architectures. In this case, I show you now two other, different examples. On the left side, you would see this single graphene nanoribbon, which is contacted by two graphene electrodes. On the right side, you would see again a single graphene nanoribbon, which is contacted by two carbon nanotubes. So these are just examples of devices that we make, and as I said, each of them has, let's say, specific purposes. One of the things I would like to highlight now is, and this is also one of the things which is very particular about these carbon-based materials, is the following. So here I take now a measurement where I also see these types of diamonds. One thing I should mention here is that most of these measurements are performed at extremely low temperatures. So this would be, well, in this case, it's 20 Kelvin, so that's minus 250 degrees Celsius. So that's extremely, extremely cold. But what we have here is that, so here we see these diamonds, so it means we have a strong quantum confinement. In this case, when we go to much higher temperatures, so this is now towards room temperature, so the highest temperature here is 23 degrees. What we see in this particular device, or several of these devices, is that even close to room temperature, we have this quantum confinement effect, which is still very present. And one of the reasons that this is important is that having quantum effects at room temperature is not so straightforward. And just to illustrate what I mean here, this is now, for instance, a quantum computer. So this is one of the quantum computers, I think, from Google. So this is what it takes to cool down your chip to the ultra-low temperatures it requires. So as you can imagine, if you want to have any, let's say, consumer application for anything which is quantum, if you have, if you need an infrastructure like this, first of all, it's very expensive, but this will never, be at your house because, it just doesn't fit, it's too big, it's too expensive. So having quantum effects, at room temperature is, of course, very important. So what I showed you here was, one type of graphene nanoribbon. In the future, what we will do is we will look at different types of graphene nanoribbons. So at the moment, we start, let's say, with the most simple ones, but there is a whole range of them that we will look at in the future. And what we hope is that, in these new types of ribbons, there will be some new physics to discover. So this is a process which would take quite some time, many years, I suspect. Along the way, there will be a few things we have to, a few challenges we have to address. Reproducibility of these devices, stability of these devices, for example. But just to put this a tiny bit into context, there is another carbon-based material which is very well known, and it's a carbon nanotube. And this one has been, underwent, let's say, a similar, let's say, evolution. So just to show you, how it went in that case. So carbon nanotubes were first synthesized in '93. It took 5 years to make them into the first transistor. From there, it took 15 years to make the first computation, and then another 6 years to make a working 16-bit processor. And this is for carbon nanotubes, which are a factor of 10 to 50 larger than graphene nanoribbons. So that means that also for graphene nanoribbons, we are probably also looking at many years of research to really have them well controlled into devices. But look, that's what research is about, right? So with this now, I would like to come back to the title slide. I more or less concluded the part about the quantum mechanics. If we now look at this picture here, I hope that you all recognize that we have here a graphene nanoribbon, which is the red stripe here, contacted by 2 graphene electrodes where we have current flowing. So this is now, pretty much what we, an actual device. So in the second part of this lecture, I would like to make a connection with thermodynamics. And to introduce that topic, I would show you this diagram here. So this is a diagram of all the worldwide energy consumption. So we have at the top, we have all the energy sources, and then towards the bottom, we have how they're being used. So that could be transportation, electricity generation, that can be heating, industry, and so on. You may not be surprised. At the moment, we still use a lot of fossil fuels, which huge carbon footprint. That also means a detrimental impact on climate. But actually, another thing which is very worrisome when you look at these numbers here is that actually most of this energy is, most of the energy is actually wasted. Most of this energy is, it's waste in terms of heat. Actually, it's mostly in terms of heat. And this is what I call here low-level heat, because it's heat which we cannot really, use too much afterwards. But would there be a way, let's say, to use this heat? If you look at the numbers, the vast majority of the energy that we produce is actually being wasted. So, this is not so efficient. And so to answer this question, whether we can somehow reuse this energy, I would like to introduce a concept here of a heat engine. So that's a thermodynamic concept. It obeys the laws of thermodynamics. And what a heat engine does is it converts heat to work. And this work can be motion, it can be electricity. One of them, I would say, most famous examples is the heat engine, so the steam engine. So you heat up the water, it becomes steam. This one drives the piston, and the pistons then drives the wheel. So, there are different types of examples. Also, for instance, the combustion engine in your car is a heat engine. But in essence, what a heat engine does is the following. You have a hot source, a hot reservoir. You have a cold reservoir, which is usually your environment. And then you have a heat flow from the hot reservoir to the cold reservoir via going through your heat engine. So your heat engine would convert part of this heat flow to work. If you have a heat engine which is very inefficient, it means that very little work would be produced, and most of it would be just heat which goes to the cold reservoir, which is just released in the environment. If you have something which is very efficient, it will be the opposite. You would have most of the heat converted to actual useful work. And if you have something which is ideally operating, you have something which we call the Carnot efficiency. This is like the highest efficiency that you can achieve. In practice, no heat engine that we have in reality is as efficient. There is always some heat loss to the environment, or things like friction, of course, also not so good for the efficiency of your engine. So back now to this energy, let's say this electricity generation. I put here an overview of the efficiencies of some of the most commonly used heat engines in power plants, or I mean other, let's say, types of heat engines to generate electricity. So on the x-axis, you have the temperatures at which it's being operated, and then you have the efficiency on the y-axis. There are two things here I would like to point out. So we have the black line. So this is the ideal heat engine. So this is the line which, at which Carnot operates. What we would see is that none of the heat engines is, at Carnot, which is fine because none of them is ideal. Nevertheless, most of them are fairly efficient. But what we also see is that the temperatures that we need to reach these high efficiencies are very large. Right? Here we're talking about hundreds or even up to 1,000 degrees Celsius. So that's a very high energy. If we would like to generate electricity from waste heat, which is usually much lower in temperature, one of the technologies that we could use is thermoelectrics. So thermoelectric generators. And if we look at the conversion efficiencies of, let's say, regular thermoelectric generators, it's very poor. So technically, using electricity from, let's say, or generating electricity from heat is possible. It's just very, inefficient at the moment, and it's also quite expensive. So at the moment, there are not too many, there are hardly any applications from thermoelectrics. So the question I would like to ask here is, we have all this quantum mechanics, we have these quantum effects. Can we somehow find something which I would call here quantum advantage? So can we have something where quantum mechanics really can, help to boost these efficiencies? And then if we look through literature, we would see things like, nanoscale heat engine beyond the Carnot limit, or extracting work from a single heat bath. So these are two things which classically, so in classical thermodynamics, are not allowed. So that means that, quantum can offer something. So how is it exactly? Let me try to answer that question. So can a quantum heat engine really operate beyond the Carnot efficiency? The answer is yes, but it requires one thing. It requires additional, what I would call here, quantum reservoirs. So these are like add-ons to the regular reservoirs, which contain some energy in one form or the other. And what happens is that in these heat engines, while these heat engines operate, you slowly drain this quantum energy. That means that, you can operate beyond Carnot, but only for, let's say, a finite number of cycles. So that means that, this one cannot work indefinitely. So yes, you can break Carnot, but you need, specific reservoirs. If you would, let's say, take these reservoirs into account and look at what they call the generalized Carnot efficiency, actually the more useful question to ask is there a way that quantum mechanics can break the generalized Carnot efficiency? Or, even better, can a quantum heat engine break the laws of thermodynamics? And there, I have to disappoint you, it's not possible. So here the answer is no. But it doesn't mean quantum cannot bring something. So there are things which are called quantum heat engines. There are two types I would like to highlight here. So the first one is the cyclic quantum heat engine. So this is something which operates similarly to your four-stroke combustion engine in your car. So you have, you go through a cycle which is driven externally. So that can mean the intake of your fuel, compression, ignition, exhaust, right? So you go through the cycle. This is a cyclic heat engine. And then on the other side, you have the continuous quantum heat engine, which is something which is, I would call, analogous to a windmill, where you just have, the windmill rotating and, you're just continuously producing electricity. So what this means in practice is that you have two reservoirs, a hot one and a cold one, which are exchanging particles. And then these can be different types of particles, but if you want to generate electricity, of course, electrons would be the most suited one. And what is interesting about these quantum heat engines is that, so there have been some predictions, so this is one in 2010, for instance, where they say that if you have a quantum system with, good energy filtering capabilities, you can create something like an ideal quantum heat engine. Nice, but, it's theory. In fact, but it has been, demonstrated. So in 2018, there was an article here where they say, where they actually demonstrated that if you have a quantum system where you have, controlled quantum confinement, you can have energy conversion which, goes towards the thermodynamic limit. So this, of course, is very nice. But this very low temperature I mentioned before, it's also very relevant here because this is even lower. This is minus 273 degrees Celsius, so it's really just above absolute zero. So again, here in terms of, let's say, applicability or usefulness, it's very limited, right? It's very good in terms of fundamental knowledge, but in terms of application, this is of course, not so useful. But you may remember from the first part of the talk where I talk about, for instance, these graphene nanoribbons, that these ones also had very good energy filtering capabilities, and that one of the, let's say, aims that we had was to have these devices operating, at least towards room temperature. And this brings me, let's say, to a big project that we're going to work on in the coming years, and this is the one that is funded by SNF and also with an ERC starting grant. And there the goal is to develop quantum heat engines based on graphene nanoribbons with an aim to generate electricity and then specifically at room temperature. So this project combines on one side, let's say, this ideal quantum heat engines from quantum mechanics, and then uses these graphene nanoribbons to make it work, let's say, to work room temperature. So this is something we're going to work on. I hope that we're going to be able to generate some new knowledge. This is not going to be directly, let's say, a product. It's not going to save the world or whatever. But I really hope that we're going to understand more how this energy conversion works, and that in the end it would be able to guide us for the design of new quantum heat engines. And what I hope actually even more is that if we go back now to the list that we had here, with the applications of quantum technologies, where quantum effects could really, boost something, like whether it's computational power, sensor sensitivity, or like security of these networks, is that in a few years we will be able to add here, quantum energy efficiency, quantum energy conversion, and that these quantum effects here, so specifically this quantum confinement, that it would really, boost the energy conversion. With this, I am at the end of my presentation, so I hope I could, convince you, at least, explain to you why I think it's useful to bring these two very different fields of quantum mechanics and thermodynamics together. And I hope that in the coming years we will be able to make more devices like these ones, that we can really try to understand this concept, these fundamental concepts in a bit more detail. With that, I thank you all for your attention. I thank you all again for being here, and I'm happy to invite you for the apéro, which is going to be upstairs in the center foyer. Thank you very much.